In previous lecture, I already discussed resolution. Let's discuss fallacies. It's a mistaken belief taken on a unsound argument. So several common fallacies arise in incorrect argument. These fallacies resemble rule of inference but are based on contingency rather than tautology. Tautology means always true and contingency means it's a mix of true and false. Contradiction means always false. If P implies Q is true and Q is true, then P should be true. It's not a tautology as it is false when P is false and Q is true. So here P implies Q is true and Q is true, thereafter P. So now P implies Q is true and Q is true. P may be true or false. It's not guaranteed that P is true. It's just opposite of modus ponens. In case of modus ponens, if P implies Q is true and P is true, then Q must be true. When P true, Q cannot be false. Q must be true. Here, in case of fallacy, P implies Q is true, then P can be true or false. In case of implication, true implies false is false, rest it is true. So here this Q is true, P can be true or false. For both, P implies Q will be true. It's called as fallacies of affirming the conclusion. Let's do one example. Example 7. Is the following argument valid? If you do every problem in this book, then you will learn discrete mathematics. You will learn discrete mathematics, therefore you did every problem in this book. P is you did every problem in this book and Q is you learn discrete mathematics. Then first statement, if you do every problem in this book, then you will learn discrete mathematics. That we can write as P implies Q. Then you learn discrete mathematics. You learn discrete mathematics is our Q. And therefore you did every problem in this book. So here is P. It's not guaranteed according to fallacy of affirming the conclusion. If P implies Q is true, P may be true or false. Means without doing every problem in this book, you may learn the discrete mathematics. So it is possible for you to learn discrete mathematics in some other way without doing every problem of this book. Basically, we are using fallacy to prove one argument is not true. So this is not true. It is false. You can learn discrete mathematics even without doing the problem. If P implies Q is true and negation P is true, therefore negation Q. It is not tautology because it is false when P is false and Q is true. Here P implies Q is true and negation P is true. Negation P is true means P is false. When P is false, for Q true and for Q false, it will be true. So negation Q may be true, may be false. It's just opposite of modus tollens. According to modus tollens, if P implies Q is true and negation Q is true, means Q is false, then P should be false. But here, in case of fallacy, it's given negation P is true, then negation Q should be true. This is not true. It's called as fallacy of denying the hypothesis. Let's see one example. Example 8. Let P and Q be same as example 7. P is you did every problem in this book and Q is you learned discrete mathematics. If the conditional statement P implies Q is true and negation P is true, is it correct to conclude negation Q is true? No. In other words, is it correct to assume that you did not learn discrete mathematics if you did not do every problem in this book, assuming that if you do every problem in this book, then you will learn discrete mathematics? Let's solve this. Is it possible that you learn discrete mathematics even if you did not do every problem in this book? So this is incorrect argument is of the form P implies Q and negation P. So P implies Q is true, negation P is true implies negation Q, which is an example of fallacy of denying hypothesis. If P value is false, then Q value may be false, may be true. It's not sure that negation Q is true, means Q value is false. So fallacy is used to prove that one argument is not valid. It's based on an unsound argument, or you can say it's a mistaken belief. In next lecture, I will discuss rule of inference for quantified statement. If today's lecture is helpful for you, please like, share and subscribe. Thank you.